Inside a modern aerospace turbine, temperatures easily exceed the melting point of the metals they are built from. Far below ground, heavy excavation equipment faces a different kind of violence, brutal friction against raw bedrock. Basic steel, a simple alloy of iron and carbon, cannot survive either of these environments. Two opposing properties: the ability to bear heavy loads under intense heat, and the physical hardness to resist kinetic deformation. Our ability to push the limits of aviation and heavy industry is completely capped by the physical limitations of basic iron. Fixing this requires an intervention at the atomic level. That intervention relies on two specific elements: molybdenum and vanadium. They sit near each other on the periodic table, yet when forged into an alloy, they behave in radically different ways. They're deployed to fight entirely separate metallurgical wars. One stabilizes metal against heat, the other fortifies it against friction. Choosing between them dictates the domain of the machine, whether it is built to survive the sky or the underground. To see why these elements produce such different results, we have to look past the macro machines and examine their electron orbitals. Molybdenum is a 4D transition metal. It has a relatively large, expansive electron cloud. Those 4D electron orbitals physically extend outward, allowing them to aggressively overlap with the orbitals of neighboring iron atoms. This intense orbital overlap creates a massive spike in bonding energy, known as a cohesive energy peak. Vanadium, by contrast, is a 3D metal. Its electron orbitals are tightly contracted and shielded. As a result, its orbital overlap with neighboring atoms is significantly weaker. This invisible variance in the physical reach of an electron cloud is exactly what determines the specific property the metal will impart to the steel. Under sustained high heat, the atomic lattice vibrates violently. Eventually, atoms physically slide past one another, stretching the steel in a process called creep. Molybdenum's intense 4D bonding energy acts as a structural anchor against this thermal vibration. This graph charts phase composition of a high-speed steel alloy across temperatures. By locking into the lattice, molybdenum forms M6C Carbides. Following the bottom axis, the M6C line remains present near 1200 degrees Celsius. They refuse to dissolve, giving the steel high-temperature strength. Without this microscopic atomic anchoring, the massive turbine generators inside power stations would deform and fail under their own operational heat. Vanadium operates on a completely different battlefield, where primary threats are physical friction, impact, and wear. The vulnerability occurs during the forging process. When steel is heated into its austenite phase, its internal grains begin to swell. Large grains make the final metal structurally weak. Vanadium counters this expansion by forming tiny, ultra-hard vanadium carbides. In a process called grain boundary pinning, these carbides act like sand mixed into wet concrete. They physically block the austenite grains from expanding further. The result is a metal with an ultra-fine grain structure, yielding extreme hardness and wear resistance for high-friction mechanical components. Vanadium sacrifices high-temperature stability for a significant increase in mechanical toughness, creating a shield capable of withstanding constant abrasive shock. Modern metallurgists rarely settle for just one of these properties. They engineer alloys designed to exploit both. High molybdenum vanadium high-speed steel is formulated as a hybrid material. This combination creates a powerful synergy. Vanadium provides brute force wear resistance at the surface, while molybdenum maintains deep structural integrity under extreme heat. By combining these elements, machines can operate in chaotic, destructive environments that would easily vaporize or shatter basic iron. Stepping back from the atomic and microscopic levels, the scale of this impact becomes clear. Our most massive achievements in aerospace, manufacturing, and heavy infrastructure rely entirely on the outcome of these unseen atomic battles. Molybdenum anchors the lattice against heat, and vanadium shields the structure against impact. Modern civilization's physical reach is ultimately a product of our mastery over microscopic electron clouds.